Hello everyone, this is N.Dilipkumar, working as Assistant Professor in Department of EC at Annamacharya College, Tirupati. So in this video, we will see about regarding the magnetostatic fields. Before moving to magnetostatic fields, let us have some parameters or the relations related with respect to a small comparison with respect to electrostatic fields. Generally, electrostatic fields are characterized by two parameters called E bar and D bar, where E bar is called electric field intensity, D bar electric flux density. In comparison to this electrostatic fields, we have the similar parameters like here. You can see the names called or the parameters called H bar and B bar. H bar is magnetic field intensity, B bar is magnetic flux density. Now let's have some relation of D and E followed by B and H. Is D bar, we can have the relation equal to epsilon E bar and B bar equal to mu H bar. This is some relation we can give for both E bar, D bar and H bar and B bar. Here, electrostatic field is produced by static or stationary charges. Is not the case the same in magnetic fields. If these charges are moving with some constant velocity, the charges maybe you can have either positive charge or even the negative charge, whatever the charge it is, you can consider. These charges are stationary, then we can have the electrostatic fields. Now, these charges moving with some velocity, or its constant velocity, there is no change in velocity. That is the point note down. It's a constant velocity. It is a generation called a static magnetic field, or the other name, magnetostatic field, is produced. That constant velocity of magnetostatic field or magnetic static field is the name we can call. From where we can get this is the constant velocity of charge. That is also called constant current flow, or we can have the other name called direct current or DC. That is how it happened. The current flow may be due to any of the cases like magnetization currents, as in permanent magnets, and electron beam currents in vacuum tubes, and conduction currents as in current carrying wires. If you would like to have some glance on examples like magnetic fields, where we can observe these magnetic fields are called from motors, transformers, microphones, compasses, telephone bell ringers. Even more we can have so many examples we can see in real-time applications. Then we can look about the basic law with respect to the magnetostatic fields, that is Biot Savarts Law. Biot Savarts Law. The statement of this law goes like this: the magnetic field intensity dH produced at any point P by the differential current element, that is IDL, is proportional to the product of IDL and the sine of the angle alpha between the element and the line joining P to that element and inversely proportional to the square of the distance R between P and the element. This is how the expression to be. The same we can have that there is a point P which is a in cross surrounded by circle. It seems the direction of the velocity of those charges or the fields maybe depends on the direction. This cross followed by circle denotes that the field will be inwards of the plane. Like with respect to this point, there is a current flow with the notation I, and among these elements, if you take a very small element which is of length dl, and joining of these 2 points seems to be a distance called r, and angle of making line joining of this distance r and followed by this point dl we call it as alpha. Now this is the magnetic field dH at point P due to current element IdL. If we move forward with this expression to remove the proportionality, we can write dH equal to KIdL sine alpha by r square. And to remove the proportionality constant K, we can substitute dH equal to IdL sine alpha, replacing K by 1 by 4 pi or 1 by 4 pi. Here, as seems to be, the numerator is the product of sine function with the two parameters I and dl. We can write in terms of cross product along with the unit vector. You can write like this, that is a dH equal to I dl cross AR divided by 4 pi r square. This is what the law called Biot Savarts Law. In extension to this, we can have the current flow may be either in different directions. Here the figure shows inward. This can be changed maybe different direction for the current. If this current flow may be outward, for the notation followed by dot followed by the circle. Now the current flow for this outward will be in this direction. It's a different case. Now we can take the comparison of this Biot Savarts law with respect to a simple example of direction of dH bar using the right hand rule or by using right hand screw rule. The rotation of the screw, let us take the example of the screw. If there is a plain board, wooden board, to tie up with some additional part of the steel body, if we'd like to tight this screw, we need to have rotate either in clockwise. Once you clockwise the screw, then it moves inwards. Or if we move the screw in or rotate the screw in anti-clockwise, it will move outwards. Based on the rotation, the direction of the screw will move different way. This is what the dH bar, the same case with respect to current flow of due to magnetic fields. Here the magnetic field intensity H bar by a small circle is shown with dot and cross signs. As the same case with respect to electrostatic fields, we can have magnetostatic fields. As charge distribution in electrostatic fields, we can have different current distributions in magnetostatic fields. The different current distributions in magnetostatic fields will be like line current, surface current, and volume current. And seems to be the figures will be like this. A conductor with flow of current I, differential element dl along the line. This is how the ideal flow of current through the conductor is I. This is line current. And surface current to be, if you take any surface, through this surface the current flow will be there, and differential element of this surface, if you take, you can have the notation k bar ds, and this surface is k bar current. And volume current seems to be conductor with some closed path, maybe closed path will exist, results in current flow, and this charge distribution will be the partial, that is differential volume of this part of this conductor will be denoted with J bar dV. Flow of the current through the entire volume of this conductor is denoted with J bar. These are three different parameters seems to be observed here for the different distribution of the current in different regions, like the current line, the line current, surface current, and volume current. We can write Biot Savarts law can be applied for all these three distributions, like h bar equal to integral I dl cross AR by 4 pi r square. In the previous screen, we have seen the dH, that is the magnetic field intensity, h bar is equal to I dl cross A bar. If we integrate on both sides, the differential element dH can be written as h bar. This is how we can write. The same I am implementing here for the line current. The same we can write for the surface, h bar equal to k bar ds cross AR divided by 4 pi r square. Similarly for the volume, h bar equal to integral j bar dv cross AR by 4 pi r square. Next, we will see about Ampere's circuit law. So, here Ampere's circuit law seems to be a very almost equal to the Gauss law in electrostatic fields. The statement for this law will goes like this: the line integral of the tangential component of h bar around a closed path is same as the net current I enclosed by the path. This is how the statement for the Ampere's law, and this expression is very much useful in current distribution, is symmetrical. If we apply the Stokes theorem for this, we apply Stokes theorem for this equation, then looks to be I enclosed equal to, as it is a line integral closed path, h bar dl can be written surface del cross h bar ds. And we can write I enclosed with respect to current density, also we can write the equation surface integral j bar ds. If we compare these two equations, that is these two, then we can have a relation from these two equations. It is del cross h bar equal to j bar. This is one of the equation in Maxwell's, and this equation we call it as differential form or point form. And one point to be noted here, magnetostatic field is not conservative. That is, del cross H bar equal to J bar is not equal to 0 here. And we can apply this Amperes law in different current distributions. That is, either line current. For the line current, if we apply, we can get the equation, that is H equal to I by 2 pi rho into a phi. And if we apply for the surface current, then we can get the equation as H equal to H bar. H bar, this is surface current. Surface current H bar equal to 1 by 2 K bar into AN cross. K bar cross AN. AN is unit normal vector directed from current sheet. We can apply this a coaxial cable also with the different radius parts of the inner conductor and outer conductor. Then you can see the magnetic flux density. Magnetic flux density is denoted with notation V bar. Here magnetic flux density B bar is related to magnetic field intensity. The relation B bar equal to mu naught H bar. Here mu naught is permeability of the free space and gives the value mu naught equal to 4 pi into 10 to the power of minus 7 henries per meter. Magnetic flux through a surface we can write as the flux denoted psi equal to surface integral B bar ds. B bar ds. Here psi is the units of Webers, and as B is denotes Weber per square meter or the Teslas. Magnetic flux lines here due to straight wire with current coming out of the plane or the page. If we take the magnetic flux line is the path to which B bar is tangential to every point in a magnetic field, and the direction B bar is taken as that indicated as the north by the needle to the magnetic compass. If we take an example of the compass, each flux line, if you take is a flux line you take, always it is a closed path and has no beginning and even no ending for this magnetic flux lines to be. And in an electrostatic field, the flux passing through closed surface is the same as the charge enclosed, that is psi equal to closed integral d bar ds equal to q enclosed. It is possible to have an isolated electric charge, but not possible with magnetic flux lines. We cannot isolate magnetic flux lines, but electric flux lines can isolate. Unlike electric flux lines, magnetic flux lines always close upon themselves. If you take an example, an isolated magnetic pole, by dividing a maximum number of divisions, that magnetic bar, if you take the north and south, we divide, then we can get one more poles of north and south is possible. The two end pieces, then we can have north and south poles. It is impossible to separate North Pole from the South Pole. An isolated magnetic charge does not exist overall to say. And total flux through total flux through a closed surface in a magnetic field is zero. That is B bar ds equal to 0. This equation refers to as the law of conservation of magnetic flux, or the Gauss law for magnetostatic fields. If we apply the divergence for this equation, then we can get the expression seems to be integral closed surface integral B bar ds equal to volume integral del dot B bar dv equal to 0, and overall we can get the equation del dot B bar equal to 0. This is the one of the Maxwell's equation, that is del dot B bar equal to 0. And the equation here, the equation surface integral B bar ds and del dot B bar equal to 0 shows that the magnetostatic fields have no source or the sinks. Magnetic flux field lines are always continuous to each other. If we see a little comparison between electrostatic fields and magnetostatic fields with respect to Maxwell's equations, both in differential form and even in integral form, you can see integral form, differential form, other name we can write as point form. Here let's look some comparisons of both. Here to write Maxwell's equations del dot D bar equal to rho v. Here we can write integral form as surface integral d bar ds bar equal to volume integral rho v dv, and del dot b bar equal to 0. Similar equation in integral closed surface integral b bar ds bar equal to 0. Here del cross e bar equal to 0. Closed line integral e bar dl equal to 0. Here, with respect to h bar, del cross h bar equal to j bar. Closed line integral h bar dl equal to surface integral j bar ds. This equation we can denote with the different names. Is the first one is belongs to Gauss law. Second one denotes to non-existence of magnetic monopole. This is where there is no division of the magnetic fields. Here, the third one is conservativeness of electrostatic fields. And the fourth one is the Amperes law. This is how we can see here with respect to magnetostatic fields with different laws, that is the Amperes law in different distributions, current distributions, line, surface and current volume, and followed by the Amperes law in both different distributions, line and surface and coaxial cable, then magnetic flux density and some relations with respect to Maxwell's equations. Thank you.